Hello everyone, my name is Jon Arrizabalaga and today I'll be defending my Ph.D. on egocentric decision making for robot autonomy. To motivate this talk, I thought there was no better way than to go to the very beginning, January 2020. At the time, COVID had not happened and this was before ChatGPT was around. During these days I was doing my master's thesis at Bosch Research. Here you see a younger picture of myself coming out of the office in Renningen, Germany. During my master's thesis, I worked on an intralogistics robot called the Active Shuttle. The Active Shuttle was intended to carry items and goods within warehouses and industrial facilities. And theoretically, this was done completely autonomously. Despite looking like a nice, cute little robot, the Active Shuttle was very powerful. It could carry up to 250 kilograms of payload. The truth is that Bosch was not able to operate it at its upper limit due to the fact that the robot relied on caster wheels. These caster wheels would make the robot get stuck when taking sharp turns. So, as a master's thesis student, my duty was to modify the control algorithm so that I could avoid these caster wheel reaction forces. To me at the time, this was a major challenge because the control algorithm did not rely on the methods that I learned during my courses, but it relied on a new framework which was unknown to me. This framework was constraint optimization. Constraint optimization goes beyond control problems and could be applied to any mathematical problem for that matter. The idea is that we've got a set of values x that we want to minimize over a given criteria or cost function. When doing that, we've got the ability to encode given requirements which come in the form of equalities and inequalities. What these do is they limit the search space upon which we are going to optimize our variable. In my specific case, I wanted to convert my control problem for the robot into a constraint optimization so that I could solve afterwards. To do that, we have to think about the trajectory of the robot. A trajectory can be represented as a collection of state and inputs of the robotical system. In this case, the states were the position and the velocity of the robot, while the inputs were the motor commands. And by stacking up all these states and all these inputs across a given time window, we can feed it into a constraint optimization that by solving it, we will be able to retrieve an optimal motion. So, in a nutshell, by combining constraint optimization with the trajectory representation that I just described, what we get is an optimal control problem. As I said, the idea here is that by solving the constraint optimization problem, we will be able to compute optimal motions for our robot. Through the cost function, we've got the ability to encourage or discourage given behaviors. In my specific case, I wanted the robot to simultaneously navigate to the goal and avoid caster wheel reaction forces. Through the constraints, we've got the ability to impose the physics of the robot, as well as other constraints, such as obstacle avoidance or ensuring that we are always within the hardware limits of our motors. So, as a master's thesis student, as soon as I understood that the only thing that I had to do was to transcribe my control problem into a constraint optimization problem, I genuinely thought that my master's thesis was straightforward. I can most definitely say that that was not the case, and to kind of illustrate that, let me show you the process that I went through. As soon as I started implementing my algorithm, I realized that I was getting solver failures. What this means is that the solver that actually is solving the constraint optimization problem, instead of providing me with an optimal motion, it was giving me an error. This error was way too hard to understand, and after trying to debug and miserably failing, I went to my mentor and I asked my mentor, why is my solver failing? My mentor looked into my code and realized that my cost function was too simple. I didn't have any additional terms. The only thing that I was telling it to do was to get to the goal. And according to my mentor, this was not sufficient. I had to help the solver by providing it a reference. This sounded like a very reasonable thing to do, so I asked him, how can I actually compute this reference that you just mentioned? And according to him, I should implement a motion planner. Fortunately, I had taken a few control and robotic courses during my studies, so I was able to go to the course material and pick my favorite motion planner. Nonetheless, as soon as I implemented the motion planner, I realized that this was not sufficient. In fact, I needed some sort of notion of time. I needed to know what was a time window upon which I was going to be optimizing my trajectory. In other words, I needed to set a final time. I did not know how to set this final time, so once again, I asked my mentor, how can I set the final time for the navigation? And he responded by saying that I could guess this by looking into my system dynamics and the specs of my robot. So patiently, I went to the engineers of Bosch, I asked them about the specs, and they indeed gave me some hints, which helped me come up with a heuristic in order to estimate the navigation time to get to the goal. So after this painful process, finally things started working out, and now I can proudly say that I had a wonderful master thesis experience. However, by the end of my master thesis, I developed this love-hate relationship with respect to constraint optimization-based control. So on the one hand, I thought that I had an unlimited power, unlimited opportunities to solve extremely complicated control problems just by feeding them into an optimization. However, at the same time, I was extremely frustrated by the amount of handcrafting and tuning required in order to make these methods work. So this dual feeling of simultaneously being very excited and very frustrated really bothered me. And in some sense, somehow sets the ground for a lot of the work that I've done during my Ph.D. So for that reason, I would like to elaborate a little bit more on my frustrations. My thought process was the following. If I have to predefine the reference and I have to heuristically decide how long it's going to take me to get to the goal, what's the point of actually solving an optimization problem? I can imagine that some of you might be a bit confused with this provocative question, so let me explain myself. This is what I call reference-driven navigation. And the idea here is that the only thing that the constraint optimization is doing, it's tracking a reference that has been pre-specified by a planner and has a pre-allocated time budget. This means that the navigation is extremely biased by the planner itself and the time allocation scheme. And if we want to achieve a given performance, we have to carefully handcraft and tune the cost function, the planner itself, and the time allocation scheme. For example, let's assume that we've got 3 different references that we've obtained from 3 different planners or 3 different time allocation schemes. Given that our constraint optimization problem is only tracking these references, depending on the reference that we will pick, the motion that we will get will be completely different. In other words, the point that I'm trying to convey is that despite solving a constraint optimization problem, the navigation is still suboptimal from a holistic standpoint. This raises the obvious question, how can we actually give the optimization problem enough power in order to compute truly optimal motions? From my understanding, the answer to this question is what I call homotopy-driven navigation. And this comes from the realization that an optimal trajectory only depends on the cost function and a choice of the homotopy class. These two items should be enough to compute our trajectories without having to rely on underlying references, time allocation schemes, or other heuristics. For example, in the illustrations that I've been mentioning, here we've got 2 homotopies. We can either pick the blue one or the orange one. Sticking to one of the homotopies should be enough to find our optimal trajectories, for example, minimum time or minimum energy. And to do that, we shouldn't rely on any sort of planner, time allocation, or underlying heuristic, as I mentioned before. Another way to see this is that reference-driven navigation sets the focus on an external reference, and thereby is allocentric. On the other hand, homotopy-driven navigation sets the focus on the robot itself and the actual task that we want to achieve. For this reason, we can denote it as egocentric. And in fact, if we look into the nature, we see that something similar happens. Here, you are seeing a cheetah hunting antelopes, and the cheetah is taking all its decisions for avoiding and running avoiding the obstacles and running in the nature from its own first-person viewpoint. And if we think about it, we humans, we operate in a similar manner. We take all our decisions from our first-person or subjective point of view. When compared to robotics, we can say that this is not definitely the case in robotics. In robotics, what we usually do is we rely on very detailed world maps that we create around our environment. We use these world maps in order to generate reference that at the final stage we will either track or follow with a low-level controller. So aligning these differences with what I've introduced in the previous slide, we can say that biology is egocentric while robotics is allocentric. Given this discrepancy, in my thesis, I've worked on laying the foundation so that we can adopt egocentricity in robot autonomy. In other words, I've focused on answering the following research question. How can we embrace egocentricity in autonomous decision-making? Trying to come up with a good answer to this question, in the past 4 to 5 years, these are the papers that I've published. Given that the talk would take too long if I would address all the papers, I've summarized them into 3 sections. First of all, I'll try to persuade you that embracing high egocentricity is actually worth it in robotics and autonomy overall. Once I've persuaded you that the egocentricity is actually worth it, I will jump into the second section where I will outline the contributions of this thesis. And finally, we will show some of the examples where these contributions actually were helpful for specific robotic applications. So with that in mind, I think we are ready to start with the hypothesis validation. But before I do that, let me introduce some annotation which I think that it's going to make it easier for you to follow some of my explanations. The first term that I want to introduce is the term of a corridor. I will use the term corridor to refer to the homotopy. When referring to the progress along the corridor, I'll use the terms either path parameter or progress variable, and this will be denoted by the Greek letter xi. The progress variable or the path parameter will be associated to a parametric path, which is a parametric function and it's given by the Greek letter gamma. The parametric path will have a moving frame associated with it, and thanks to this moving frame, we'll be able to project the Cartesian coordinates of the dynamical system into the spatial coordinates. The spatial coordinates are the progress along the path, xi, and the orthogonal distance to the closest point in the path. Having introduced the notation, I think we are ready finally to get started with the first section where we want to validate our hypothesis. To do that, we will try to question if we should actually pursue egocentricity at all. In order to answer this question, we will rely on a very specific problem. Nonetheless, this problem will serve as a springboard in order to generalize some of the components and contributions that I'm about to present. We've chosen the problem of time-optimal navigation for quadrotors. And this is not an arbitrary problem. We've picked this problem for 2 specific reasons. The first one is that aiming for time optimality, it's a great way to see if egocentricity is able to achieve the aggressiveness and the agility that we want for our robotical systems. The second reason is that we've picked quadrotors because they allow us to operate in the 3-dimensional space. This relates to the fact that a lot of the contributions that we will present are considerably more difficult in the spatial domain, and therefore picking a platform that operated in this domain was of paramount importance. To put this problem a little bit into the context of the notation that I introduced, let me highlight that the homotopy in this case is the corridor that we build around the racetrack. In other words, we are going to be calculating time-optimal trajectories around an artificial or virtual corridor that we constructed by inflating the racetrack. The racetrack itself, it's going to be the parametric path. And given that the homotopy and the parametric path are very well defined, we will represent the quadrotor system dynamics in the spatial coordinates. What this means is that the position and the velocity are not going to be represented in the standard Cartesian coordinates, but they are going to be given in the spatial domain. This implies that the progress along the path xi and the orthogonal distance to the racetrack are going to be part of our states. By combining all these three components, what we end up having is an optimal control problem that is very similar to what we solved or what we proposed at the beginning of the talk. However, there are three specific factors that make it slightly different. The first one is that in our cost function, we will maximize for progress. Progress maximization, it's a well-known proxy for time minimization. And leveraging the idea and the fact that progress is within our system states, what we will do is we will maximize for progress. The second ingredient is that in order to ensure that the quadrotor remains within the homotopy, we will constrain the orthogonal distance to the racetrack to be within the cross-section of this homotopy. And the third and final ingredient is that we will be limiting the true physical inputs of the system, the rotor commands. By doing so, we will have the ability to push the robot to its limits due to the fact that we will have access to its full dynamic envelope. So, by combining all these three ingredients, what we end up having is an optimal control problem, which is very hard to solve because it's non-convex. Nonetheless, thanks to the great solver Akaros, we will be able to solve this problem in 20 milliseconds. That converts to roughly 50 Hertz. So the key takeaway from this slide is that thanks to egocentricity, we've been able to convert a very hard problem, which is time-optimal navigation for a highly nonlinear system, into a problem that we can solve in real time. To validate this, we compared it against the ground truth solution, so basically the real time-theoretical optimal solution. This optimal solution is given in blue, while ours is given in yellow. And we can clearly see that the, let's say, ground truth optimal solution is extremely close from our solution. The big difference is that the ground truth solution is computed offline. It required up to an hour of computation, while ours in yellow runs in real time at 20 milliseconds without relying in any offline compute. In other words, egocentricity has allowed us to achieve near time optimal performance in real time. We did double check that we were not overfitting to our specific racetrack, and we compared this to other racetracks with different layouts and with different levels of difficulty. And here we saw that regardless of the homotopy's complexity, regardless how hard and complex the corridor was, we still remained being time optimal. So we started this first section questioning if we should pursue egocentricity. After seeing these two examples, we've seen that egocentricity has allowed us to compute very complicated motions with the ability to exploit the available space in a computationally tractable manner. For that reason, I believe that the answer to this question is yes, 100%. Egocentricity is a paradigm, it's an idea that is worth being pursued, and we should try to make our best efforts to generalize it beyond drone racing to the broader robotic setup. With that, I will conclude this first section. I will assume that we have validated our hypothesis, and I will move on to the second section, where we are going to be talking about our contributions. To introduce our contributions, I would like to briefly get back to the drone racing example, because the shortcuts that we took in order to make this example work are the exact same limitations that forbid us from generalizing these ideas into the broader setup. Therefore, emphasizing and highlighting these limitations will provide us with an outline of the contributions that I'm about to present. The first limitation or shortcut is the spatial representation of the system dynamics. In here, in order to come up with the equations of motion of the quadrotor system in the spatial domain, we did it in such a way that was specific to the quadrotor and did not generalize to arbitrary dynamical systems. For that reason, in the first contribution, we will be talking about how to generalize the spatial representation to any arbitrary dynamical system. The second contribution is regarding the moving frames. We've mentioned that the moving frames are important in order to convert the Cartesian representation into the spatial representation. In our specific case study, the algorithms that we used in order to compute these moving frames were specific to the racetracks that we were operating. And you can imagine that if we want to use these moving frames in any given path, we basically would run up into numerical difficulties or singularities. So therefore, we will have to rethink how to compute a moving frame for any given parametric path. And in the final contribution, we will be talking about environment representation. Arguably, this is the most intuitive limitation of our drone racing example. In here, we were assuming that the available space was described by tube-shaped or tunnel-shaped homotopies. However, if we want to generalize the ideas of egocentricity to the broader setup, we need to have the richness and the expressivity in order to describe random environments. And to do that, such homotopies are a limitation. For that reason, we will be thinking about which is the most appropriate environment representation for our problem. So hopefully, by addressing these three questions, we will make it a little bit easier for roboticists and practitioners to adopt an egocentric approach in their own research and in their own robotic applications. With that, in the remaining of the talk, I'm about to proceed by answering each of these questions. Let's get started with the first one. In the first question, we are dealing with the fact that we want to generalize the spatial representation to any dynamical system. To do that, let me get back to the illustration of the intralogistics robot. If we were to generalize this to the broader setup, the mobile robot, the intralogistics robot, or the drone would become an arbitrary dynamical system. And the center line of the homotopy would be a parametric path. As a reminder, the parametric path is a parametric function that takes the path parameter as the input and outputs the Cartesian coordinates of the center line of the homotopy. If we want to adopt egocentricity, we've already seen that what we have to do is we have to project the dynamical system into the parametric path. And the way to do that is by augmenting the parametric path through a moving frame. The moving frame is also a parametric function which takes the path parameter as the input and outputs the rotation matrix associated to the moving frame itself. In the notation, we've already mentioned that the moving frame will allow us to convert the Cartesian coordinates into the spatial coordinates. And hopefully, after seeing the example of drone racing, you agree with me that having access to these spatial coordinates allow us to compute very complicated motions that we would not be able to do in the Cartesian domain. So if we want to do planning, control, and decision making in these spatial coordinates, we need to know how these coordinates evolve on time. In other words, we need to know which are the equations of motion for these spatial coordinates. And this is exactly how we've addressed this first contribution. What we've done is we've derived these equations of motion for these coordinates. In order to derive these equations of motion, we assume that we know two things. The first one is that we know how this dynamical system is moving. In other words, we know what's the velocity of the dynamical system. The second assumption that we take is that the parametric path is described by the parametric speed, the moving frame of the parametric path, and the angular velocity with respect to the moving frame. So, taking as granted that this information is given, we derived the equations of motion for the spatial coordinates. These equations of motion are generic in the sense that they are applicable to any dynamical system, and they are agnostic to the underlying moving frame. They are compatible with any moving frame. If you are wondering how we derive these equations of motion, there are two alternative approaches that we can take. We can either do it through kinematics in a very similar way how we would do it in a mechanics course in undergrad, or we could do it from an optimality standpoint. And no matter which of the options we take, we will end up having the three equations of motion described in the gray box. As I just briefly mentioned, one of the key features of these equations is that they are applicable to any moving frame. What this means is that the user is responsible for picking the most suitable frame according to his or her needs. And this raises the obvious question, which frame should we actually pick? Which is the optimal frame in order to be used with these equations of motion? I genuinely believe that there is no universal answer to this question. I think it's a little bit specific to the actual application that the user has. But in our specific case, where we are focusing in optimization-based navigation, we do have a first favorite. And in order to kind of present this option that we present or that we pick for the moving frame, we will have to move on to the second contribution. Before I do that, let me summarize what we've done in the first contribution. In here, we've presented the equations of motion for the spatial coordinates in such a way that we can use them with any dynamical system and any moving frame. This has opened up the question of which frame we should pick, and in the second contribution, we will choose a frame which is especially suitable for optimization-based navigation, planning, and control. So, as I just said, in the second contribution, now we will be talking about the moving frame. Which moving frame should we pick, and how are we going to compute it? Before I give answers to these questions, I would like to spend some time showing you which are the portfolio of options that we had in the literature before answering this question and coming up with our own moving frame. When going over this portfolio of options, I will evaluate them according to three criteria. First of all, I will see if they are singularity free. Second of all, I will evaluate if we've got access to gradient information and if this gradient information is continuous. And finally, I will criticize them depending on their simplicity or their complexity. So the first frame that we've got in the portfolio is the Frenet-Serre frame. The Frenet frame, it's, I would say, the most popular frame in the literature. And the reason for this is that it's extremely simple to implement and very lightweight. Due to this simplicity, we can say that it has taken all over the robotics and control literature. But this simplicity comes at the cost of singularities when the path becomes a straight line, and also on the fact that the gradients are all over the place due to these singularities. Given the popularity of the Frenet frame, these issues have been very deeply studied, and an immediate solution to that is the parallel transport frame, or the PTF. The PTF, it's also a well-established frame that, as I said, provides an immediate solution to the limitations of the Frenet frame. It fixes the singularities, but in its pure form, it's not able to provide any gradients. And a third option that we've got is the Euler-Rodriguez frame, or the ERF. The ERF definitely is not as popular as the Frenet frame or the PTF, but it somehow has a mathematical beauty that the prior ones don't. The ERF is well defined, which means that there are no singularities, and it can also provide the required gradient information. However, the issue of the ERF is that it relies on Pythagorean hodograph curves. These are a subset of polynomial curves which are extremely cumbersome to work with, and for that reason, using the ERFs, it's definitely not straightforward. As an anecdote, for a large chunk of my PhD, I genuinely thought that the ERFs were the ultimate solution, but at one point I had to genuinely accept that just using these ERFs was going to be too difficult for the community, and I had to give up. So, kind of through this brief summary, I hope that you clearly see that none of the options that we've got in the literature fulfills all three requirements. And this motivated us to come up with our own frame, which is a variant of the PTF, and we denote as Egocentric PTF or ePTF for short. This frame, because it was designed to do that, ticks all three boxes and fulfills all our desired criteria. This means that it's well defined, so it is singularity free. We can obtain the gradient information, and it's guaranteed to be continuous up to the second order, and it's extremely simple to implement. So this was our thought process in order to kind of propose the ePTF as a moving frame for optimization-based navigation within egocentricity. With that, I think we are ready to look into how we actually can compute the ePTF. Let's assume that we want to assign an ePTF to the parametric path given in blue. The first thing we have to do is we have to discretize the parametric path and collect the gradient information up to the third order of the path. We feed this gradient information into two very simple algorithms, and out of the algorithms, we will get the moving frame associated to the ePTF as well as its angular velocity. And this information, we can either use, let's say, the zero gradient-based information, but if we would like to, we could also get the first and second derivatives of the ePTF and its angular velocity. So in other words, we've got the ability to compute the frames and the angular velocity as well as the derivative information. As I've mentioned in the previous slide, this frame was designed such that all this information was guaranteed to be well defined and C2 in the sense that it could provide gradient information up to the second order. And thanks to these features, we can use this frame in optimization, learning, or any other decision-making algorithms where gradients are required. Another feature that also we briefly mentioned in the previous slide is the idea that the underlying algorithms operating under the hood are extremely simple to implement. They can be written down on 50 lines to 100 lines of Python code. So in a nutshell, we end up having the benefits of the ERF, so the nice mathematical properties of the ERF, while remaining as simple as the FNF frame or the PTF to be implemented. With this, we've reached the end of the second contribution, and we are ready to move into the third contribution. In the third contribution, we are going to talk about how to represent the environment. This comes from the fact that if we want to embrace egocentricity in the most generic sense, we need the ability to describe random obstacle-free environments. And to do that, we cannot rely on tube-shaped or tunnel-shaped homotopies. We've exactly addressed this need in this third contribution, and we've done this by focusing on a method which generates corridors. Our method, our corridor generator, takes the parametric path and a point cloud describing the environment as inputs, and outputs a corridor which is guaranteed to be collision-free, smooth, and differentiable. To achieve this and to be able to compute these magnificent corridors, our method relies on three main ingredients. The first one is that the cross-section of our corridor is chosen to be an off-centered ellipse. What this means is that the ellipse can change its shape, the size, as well as it can have an offset with respect to the parametric path. In the second ingredient, what we do is we parameterize the off-centered ellipse by Chebyshev polynomials. And doing this will allow us to sweep the parametric path from the beginning to the end. And in some sense, this is going to be what gives the shape to our corridor. The shape and the size are going to be fully dependent on the coefficients of the Chebyshev polynomials. Depending on the coefficients that we've got, the corridor's shape and size will change. In the third ingredient, we compute these coefficients by solving a volume maximization problem that somehow will find the respective coefficients of the Chebyshev polynomials. In other words, by solving this convex optimization problem, what we end up doing, we end up finding the coefficients whose corridor is going to have the maximum volume. This optimization problem, as I briefly mentioned, it's going to be convex, which means that it's very easy to solve, and we've got a strong guarantees that we are going to be able to find a solution for these problems. In here, I'll not provide the details, but the idea is that we were able to represent this problem as a linear program, which is the best, let's say the most mature optimization problem that we've known for the last decades. Thanks to representing as a linear program, we are able to get very good compute times. We are able to solve this optimization problem in between 50 and 200 milliseconds, depending on the problem's complexity. This translates to roughly operating between 20 to 5 Hz. What this means is that we are able to use this corridor generator in real time for any autonomy stack of robotics. So in a very brief nutshell, this is the ingredients and the idea behind our corridor generator. In order to kind of get you excited about the actual potential of these corridors, let me show you some of the examples that we obtained when evaluating this method. In here, we are focusing on the Kitty dataset. The Kitty dataset is a dataset from autonomous driving. And at this specific instance, we will be focusing on a case where the car is located at a bifurcation where we've got two options. We can either go left or we can either go right. What we ended up doing is we computed the corridors associated with both options. The option for the left lane is given with the green corridor, while the option with the right lane is given by the pink corridor. And as I was describing, here we conducted a very detailed analysis and comparisons with the state-of-the-art methods. But due to the fact that somehow we want to remain this presentation within a reasonable time constraint, I'll leave this up to you to read the paper. What I want to focus on here is a little bit more on the qualitative aspect of these corridors. Visually, it is apparent that both corridors encompass the entire width of the road and show the ability to adapt to the different actors that appear on the road, for example, the cyclist, the cars, and any other agents that might be on their way. So in other words, these corridors are an extremely rich representation of the obstacle-free environment. And having such high fidelity is something that very well could be exploited in the egocentric ideas that we've been introducing. So with that, I conclude the third and final contribution. And we've reached a point where we have finally covered all the three contributions. I believe that by doing that, we've made it a little bit easier for roboticists and researchers to adapt an egocentric approach in their own research and in their own robotic applications. Given that this presentation mostly was given from a conceptual and theoretical standpoint, I thought that the best way to wrap up this presentation was by providing you with a glimpse of how some of the contributions can be useful beyond egocentricity. To do that, I will kind of cherry pick some of the research projects that I've been collaborating and working on during my PhD, and I will try to show you how some of these ingredients were useful and beneficial for these research projects to actually become and kind of solve a real-world problem. These problems will span the entire breadth of robotics. They will go from theory up to application-oriented and system-oriented solutions. So starting at the theoretical side, one of the projects that I worked on during my PhD was low-level control for pose control. So the idea here was that we wanted to simultaneously control the position and the orientation of our robots. In the original paper, I wrote down the controller to do that, and I provided the global stability guarantees required to make the controller work. Very recently, we adopted this idea with some of my collaborators at WPI, with Fer and Wanri, in a real drone, and we achieved magnificent results. These results are about to come up in a RAL paper, so feel free to read it and to enjoy those results. We also accounted for some of... so before I go to the next project, maybe let me highlight that when doing that, when kind of adopting these post-control concepts, the spatial coordinates and the ePTF, especially in my first theoretical paper, were definitely very useful in the theoretical derivations that I did. The second kind of group of work that maybe benefited from my contributions was motion planning. During my PhD, we wrote a few motion planners that kind of leveraged some of the ideas that I've been introducing. These were applicable both to robotics and to space exploration. Starting with robotics, some of these ideas were exploited in such a way that we leveraged the corridor generator in order to introduce the notion of volume into the planning aspect. And in the side of space exploration, a fun project was the one where we parameterized the near rectilinear halo orbit around the moon with the ERF moving frame. And finally, arguably one of the most exciting projects that I worked during my PhD was the transportation of liquids with robotic manipulators. In here, we developed a pipeline that was able to transport liquids without sloshing or without any spilling. And when doing that, once again, the spatial coordinates and the ePTFs were definitely useful. So I hope that with this slide, I've been able to convince you that the contributions that I presented not only are useful for egocentricity itself, but they can also be applicable to very specific robotic applications beyond egocentricity. With that, I finally have reached the end of my talk. So if you are not able to follow my explanations, or if I was talking too fast, please pay attention here, because this is the place where I'm going to summarize everything. We've started the talk by identifying the need to embrace egocentricity into robotics and autonomous decision making. Instead of just jumping right into the problem, we've sanity checked our hypothesis by comparing it or evaluating it in a drone racing example. After actually seeing that thanks to egocentricity we are able to compute very complicated motions, we've been motivated and propelled to generalize this to the broader robotic setup. To do that, we've presented three specific contributions. We've derived the equations of motion for the spatial coordinates. Then we've proposed a moving frame that is compatible with these equations of motion. And finally, we've talked about how to represent the environment in such a way that we've got a high fidelity representation while remaining computationally tractable. And finally, very briefly, we've shown how some of these contributions can be useful beyond egocentricity to specific robotic applications within robotics and autonomous decision making in general. So with that, I conclude my presentation. I thank you, the listener, for getting so far and listening to my presentation. And before I finally close this presentation, there is one last thing that I would like to mention. A Spanish philosopher once said, "I am I and my circumstance," and this is definitely the case for the PhD work that I've just exposed to you. None of this work would have been possible without the help and assistance of a lot of collaborators, friends, colleagues, lab mates, and other people. So for that reason, there is three different groups of people that I want to acknowledge or thank. The first one is, of course, my advisors and my committee members. All of them are people I really look up to, and it was an absolute honor to have them in my committee. And somehow, without their guidance, none of this work would have been really executed. So for that, I'm really thankful to them. Second of all, I've been lucky enough to be at multiple places during my PhD, and all these places I've been exposed to wonderful lab mates, wonderful colleagues that have shaped a lot of the work that I've done. So for that, I hope they know that I'm extremely thankful. A lot of the content that I've presented somehow is shaped by their inspiration and by their presence. And of course, the third group of people that I wanna thank, it's family, friends, and roommates that I've done or I've met along this PhD journey. I have had lots of fun, and without their moral support, none of this would have happened. So to all of you, thank you very much, and I hope you enjoyed the presentation. Thank you so much.